Hey guys, I know that usually for a review page, you don't have to have a video, but honestly, it's super important that you watch this video and check your homework from the last section that you did before you go into the review so that you know that you're understanding everything, okay? So, I'm gonna try to remember all the answers that I just got because I was going over these examples and the practices and everything like that. So just make sure that you take out your stuff, you're checking it with me. Now look, you know that for the most part, I like to be working with pictures for you guys instead of you sending me in your work. The most important thing is that we are getting the pictures. So if you do send in the physical work, okay, está bien. But most importantly, it's the pictures. But I'm mentioning that in this video because you are supposed to turn in your Chapter 3 review for science for the end of this week. And the next week we go into Chapter 4. But however, that first section of Chapter 4, when I do a video, I'm going to go over some of the Section 3 review, the Chapter 3 review. So if you do send in physical homework, listen carefully. Don't send in your Chapter 3 review yet. Don't send in your Chapter 3 review so that you can take it out during the video and you can check and make sure that you're understanding those concepts, okay? So here we go. Look at practice 3.5. A we already did, so we're on 3.5. B, sorry. Look at 3.5B. Number 1. If 260 newtons, if a 260 Newton rock is lifted with a lever having an IMA of 4, how much force must be exerted under ideal conditions? Over what distance would this force have to be exerted if the rock is to be lifted? Okay, so it has an IMA of 4. How much force must be exerted? Let me find my calculator. So what you're gonna do is, first of all, we know the IMA is 4, which means that the machine is going to be doing 4 times the amount of work for you. So the machine was pushing a 260 Newton rock up the thing, right? So if it's lifting a 260 Newton rock and it's doing 4 times the work for you, then that must mean that all you have to do is 65 newtons because you use 65 times 4 to get 260, which is what the machine was doing for you. So over what distance would this force have to be exerted if the rock is to be lifted 0.5, okay? So let's show you that on the board. So we're gonna be using the formula F1D1 equals F2D2. Remember, that is the work formula found on page 72, okay? So we go, force is 260 and you wanna move it 0.5. Remember that if you are doing that, you're always gonna have a longer distance for what you have to input on that lever. So then the force that was moved is 65, and then we don't know the distance. So we go 260 times 0.5 is gonna be 130, right? Divided by 65 equals 2. So 2 meters is what the distance is for how much the force has to be exerted to get 260 newtons to move 0.5 meters, okay? Look at number 2. What is the IMA of a 1.5 meter broom if it is held at the very top and the input force is 0.6 meters below the end of the handle, okay? So we go over to the IMA equation, right, of, let's see, IMA equation that I'm looking for the broom. Let me find it. These first couple questions I did like last week. So let me look at it. Oh, right here. Look at page 75. Okay, page 75, it says input distance over output distance. So the input distance is gonna be 1.5. Your output distance is gonna be 0.6 because that's where the force is applied. So your IMA is gonna be 2.5, okay? Look at example 3. What is the IMA of a wheel and axle if the input radius is 26 and the output radius is 2? Well, that equation is going to be on page 75 as well. Input radius over output radius, so that's going to be 26 divided by 2, which is going to give you 13. Okay, if a helicopter rotor has an input radius of 5 and an output radius of 4, what is its IMA? Same thing we just did in number 3, as 5 over 4, so it's going to be 1.25. Does a helicopter rotor multiply force or multiply speed? Well, you just go right over to page 75, and it says right here, if the input, this is the last sentence on the second paragraph, if the input is applied to the axle instead, as in the rear wheel and sprocket of a bicycle, the blade of a lawnmower, an airplane propeller, or a helicopter rotor, speed and distance are multiplied. So it's speed, not force, okay? And number 5, a block and tackle with 8 rope segments supporting a load lifts an 18.0 kilonewtons load with an input force of 9 kilonewtons. What is its IMA and what is its AMA? Well, look, I'm going to read you this paragraph. It says a combination of, the paragraph's on page 76 right here, the block and tackle. A combination of one or more fixed pulleys and one or more movable pulleys is a block and tackle. In the block and tackle, the movable pulleys multiply the input force while the fixed pulleys change its direction. Ideal mechanical advantage of a block and tackle equals the number of rope segments supporting the load. So it's literally what? If there's 8 rope segments, your IMA is 8. Okay, for example, a block and tackle with 4 rope segments supporting the load has an ideal mechanical advantage of 4. If the output load is 80, ideally an input of only 20 applied to the rope will raise the load. But the rope must be pulled 4 meters for every 1 meter the load is raised. Because of the large amount of friction in a block and tackle, AMA is usually much lower than IMA. Efficiencies are low, typically ranging from 40% to 60%. And we can see that the evidence is right there for that, because if the IMA is 8, but how do we get the AMA? The AMA is still output force over input force. The output force is 18, the input force is 9, so 18 divided by 9 is 2, which means the AMA is way lower than the IMA because of the friction involved in a block and tackle. Okay, it really slows everything down. So those are practice 3.5. Look at practice 3.5C instead of 3.5B. Okay, look what it says. If an inclined plane 4.5 meters long. Oh, well, my camera did something really weird, so I hope it doesn't do it again. And it erased the last thing I said. So the AMA, how do we find the AMA? It's still 18 divided by 9 because it's output force divided by input force, which we can find that equation on page 73. And so it's 18 divided by 9, which is 2. So you can see that the friction really does do a lot to it, you guys, because the friction brings it down all the way from 8 IMA to 2 AMA, the actual mechanical advantage. Okay, so let's look over on page number 79, 3.5C. An inclined plane 4.5 meters long is used to place a 4,800 Newton piano in the back of a pickup truck 0.75 meters off the ground. What is the AMA of the inclined plane? Okay, if you look at page 77, you're going to see that the IMA of an inclined plane is length over height. Okay, so you're going to do the length is 4.5 and your height is 0.75. So your ideal mechanical advantage is going to become 6. So how much force is ideally required to move the piano? Because you have to move, the piano is 4,800 newtons. So you're going to divide that by 6 and you're going to need to apply 800 Newton force. Okay? Number 2, what is the IMA of a wedge? 2.0 centimeters thick and a and 10 centimeters long, okay? Well, in that case, you look at the wedge. That's on page 78. It's length over thickness, so that's 10 over 2, so your answer is 5. And number 3, a jack screw has a 40 centimeter handle and a pitch of 0.8. What is its IMA? Okay, look at page number 78 again. Your IMA for a screw is 2 pi times r over the pitch, right? So you have 2 times 3.14 times, this guy has a 40 centimeter, that should be the radius. Okay, 40 centimeter handle, so we call that the radius. So let me just make sure about that because I can't remember if you divide it by 2 or not, but I don't think you do. No, you don't, okay. And then your pitch is 0.8. When you put all that into your calculator, you're gonna get an IMA of 314. Okay, an IMA of 314, which is a really strange number for an IMA. But again, they say that the IMA is high and the AMA is low because there's so much friction when you're using a screw. Okay, so now let's look at concept review 3.5. Concept review 3.5, let's go over some of those. What is the ideal mechanical advantage? How is it different from actual mechanical advantage? You can see that on page 72. Ideal mechanical advantage is when you don't take friction into consideration. So that means that if there were no friction in the world to slow things down, this is how much work your machine would be doing for you. It would be doing 4 times your amount of work, 3 times your amount of work, whatever it is. But AMA brings into account friction, meaning that in a real world, the actual mechanical advantage, you have to take friction into consideration, and it's going to be a lot less. Number 2, what is greater under ordinary conditions, work input or work output? Again, you're going to look at page 72 and see that its work input is always greater because in an ideal world, the work that you put in should be the work that you get out. This is without machines, right? No mechanical advantage. The work that you get in, it should be the work that you get out. However, because of friction, you're always gonna have less work that you get out than you put in with the machine or with you, okay? Number 3, describe the 3 classes of levers based on the locations of the input force, output force, and fulcrum. We went over the video on that one, and it was explained, so you just needed to repeat it. That's on page 74, or the video that I sent out that day. Number 4, which simple machine can be considered a circular lever? That's going to be on page 75. It's the wheel and, no, pardon. Yes, it's the wheel and axle. It's the wheel and axle. That is said on page 75. Number 5, what type of machine combines fixed and movable pulleys? That's your block and tackle. Page 76 tells you that. Number 6, which simple machine consists of a sloping platform that enables an object to be raised without lifting it straight up? That's the inclined plane on page 77. What simple machine can be visualized as an inclined plane wrapped around a rod? That is page 78, the screw. Number 1 on application. Why can a baseball player hit a ball farther when he grips the bat at the bottom of the bat than if he were to move his hands halfway up the bat? Okay, interesting question. You guys might have all different answers because you're trying to just make like a scientific hypothesis, basically. But what I'm going to tell you is that the bat is a lot like the class 3 lever, okay? We can see that because of the fly swatter right here. And so I believe it's because if you move your hand, if you have a bat like this, right? You have your hand down here, your input distance is going to be very, very big, which means that your IMA is going to be big. Because your IMA is input distance over output distance. But if you move your hand up halfway, what did you just do to your input distance? You cut it in half. And if you cut in half your numerator, then your answer is going to be smaller, which means your IMA is going to be smaller. So that's what I said. Number 2, a screwdriver handle has a diameter of 2.6, the blade is 7, an input force of 15 is applied. What is the output force assuming ideal conditions? And of course I didn't write how I did this, so let me just make sure I put the right thing up on the board. My answer was 17.49. I don't know what your answer is, but I'm gonna show you how I got it. Okay, so I used the equation of the IMA for a screw, right? I did 2 pi times the radius, well the diameter is 2.6, so the radius is 1.3, the half of it, right? Divided by 7, which is the blade, which is the pitch in this instance, and I get 1.1 something. So that when they say that you put in a force of 15, what is your output force? I'm going to multiply this times 15 because it's going to be doing 1.1 of the work for you. That 1.1 makes sense because they said that the mechanical advantage is low on a screw, right? And so then you do 1.1 times 15 and you're going to get 16.5 or 17.49 because I had more decimals going there. Okay? So it's just a little bit over 15 is what it should be. Okay? So those are your answers for this part. And if you have any questions, just let me know. I know some of them are a little bit confusing and it's not like you need to get a perfect score on them, but we're being introduced to this, and if you understand my explanations, then we should be good to go.